Okay, hello everyone. Welcome to the CASBA seminar. And today is my great pleasure to introduce Salah Talamali, who joined us from Sheffield. I know him from quite a few years because after he completed his master in Algeria, École Polytechnique of Algeria, in Algeria, he moved to Sheffield to do again another master in order to be accepted as a PhD student. And during that time, he decided to do the master's thesis with me. I saw how great he was, and so I offered him a PhD together with James Marshall. We offered him a PhD position that he did exceptionally well in a focus on swarm robotics at that time. And after that, he moved to UCL, where he focused on the topic that he will speak to us about. That is this spatial sound modulation. You will see it looks really like magic. You can really do spatial tricks with this new technology that will probably appear in all our life soon, but then could be also useful for some of our experiments. But then after UCL, now is a return to Sheffield, first with a strong teaching position where he got a few awards on being one of the best teachers of the university. And we might, sorry, I increase a bit the expectation, but we will see now his presentation skills. And now instead he moved to a fully research position. So he's back. We are really happy to have him back to research. And so I think you might try, especially all the experimental biologists in the room, keep your ear attentive to see if you can find a link with what the technology proposes, if it can be useful for your studies, because it might be interesting to create a collaboration with Salah and see if we can attract him here maybe to bring this technology with him and use it for our stuff. So I don't take further time. I leave you the stage. Welcome, Salah.
Yeah, thanks, Giovanni. Thanks for having me here. It's really my pleasure. Thanks also for the organizer, Alexandra and Daniela, for making this happen. So today I'm about to tell you about research I have done at UCL. It was a bit unfortunate. I had to work from home. I'm so lucky I started the postdoc during COVID. So I never met my colleague. I met them once when I gave them back my laptop. And today I'm going to tell you about this research. So Giovanni invited me here thinking that this research could be combined with the system, especially the virtual reality system you have here for animals. And I'm going to start with this scenario. So let's imagine you pass by your colleague's office, you look and you find them apparently interacting with unseen objects. I do this. I like to have a look sometimes. And you say, oh, wow. You give it a second look and they don't have any VR headset or VR glasses. What will be your thoughts at that point?
It's crazy.
Let's not jump to conclusions, because I'm about to tell you about devices that may help them interact with unseen objects. And as an early spoiler, these devices use ultrasound or use sound waves. And to start, let's recall how sound waves propagate. So sound propagate through longitudinal waves, and as these waves travel through a medium, let's imagine air, they move the particle of air and they create zones. They bring these particles sometimes together, creating zones of compression, and sometimes they split the particle of air, creating low-density particle zones. And this change in pressure is picked up by our ear. So we have mechanisms in our ear to convert that into signals sent to our brain so we can pick up the sound. So if you can let multiple sound waves interact together, you can affect the pressure of air in the way you want. So here, if I put two speakers facing each other and let them emit sound waves that travel on opposite direction, I can create what is called the standing wave. As we can see, the resulting wave will be a wave that just flips its amplitude, but there are points that don't change in pressure. Why we call it standing wave? Because it's not traveling, it's staying there. So this is one example of waves interacting with each other. Another interesting example of creating or adjusting the pressure of air is when you put multiple speakers. So you can put them like here in an array configuration, or you can put them as a bowl configuration. And by controlling the delay or the phase delay between the sound wave, you can let all the waves arrive at the same point at the same time, such as here, and you create what is called a focus point. So all the sound waves will meet together, and they add with each other, and they create a high pressure at that point. In this case, from now on in this talk, you will hear me speaking about spatial sound modulation. And it is this technique of using sound emitters to vary the pressure of the air around them. And one key thing is to find the delay between these waves. And that's called phase retrieval. So to let them all meet at the same point, you need to find the delay of each speaker. So they all meet at the same point. And if we say pressure applied to a surface, what we say in physics, we say a force. So the sound wave, when they interact with objects, they exert on these objects what we call acoustic radial forces. In this study, for example, they put a circular or sphere object in a pressure field that they created using standing waves. And for small objects, these radial forces will move that object in between the high pressure point of the standing wave. Instead, if you put a big object in this pressure field, that force will move it to the zones with high pressure. And how this force affects object depends on many things. It depends on the size of the object, the shape of them, but also on the acoustic properties of these objects. So people have used these properties of sound to create cool application or useful application. For example, Long and colleagues here have used this focused sound to let people feel objects, virtual objects that are in scene. So what they did is they have a setup where they track a hand. They have a virtual object in an environment, for example, here a cube. And as the user moves their hand, through the hand tracking, they can capture the points of intersection of the hand with that virtual object. And then what they do, they can create multiple focus points of sound, not focusing the sound all at the same point, but playing with those phase delay of the speakers to get sound focused in multiple points. And what they do, they keep turning these points, this pressure, on and off 200 times per second. The reason for that is that our tactile receptor on the human hand are only sensitive to change in the pressure, not to the pressure itself. So what they do, they know that the human's tactile receptor are able to sense things if they change at a frequency of 200 to 300 kilohertz. So they turned on and off this speaker 200 times a second. And you can see the effect of that on an oily medium. But also they have done the same thing, but using one focus point. So what they do, they create that one focus point and they keep moving it as a circle, right? And they do the full circle 200 times per second. So the question you'd be asking, how to get all the sound focused on these points. So what did we say before? How are we able to focus sound waves in a point, for example? So what we said earlier is that if I want to get sound focused all on the same point, I need to find the delays between the sound waves to make sure that they arrive at that point all at the same time. So they add up together, creating me this zone of high pressure. So what they have here, I'm trying to make it simple. There is a bit of a lot of equations, and I don't want to bother you this morning. So what they do, they have a desired focus locations, and they have models to compute the pressure field that these speakers together will create as a function of the phases of each speaker. And they add some constraint to adhere to the transducer specs, their power, etc. And they combine this into an inverse problem where they solve. So they have an equation that contains the delays of the speaker, the phases, and they solve, and they have a desired sound field they want to create, and they solve this inverse problem on the computer to find those delays. One challenge is you need to do it really fast. If the user is moving their hand and the intersection is changing and the point of focus is changing, you need to do this computation really fast. So the method you use need to give you that speed. So another application of this control of sound pressure is levitation, acoustic levitation. So using the sound pressure, you can keep objects suspended in midair. So let's not think of big object as just really small object of lightweight. That's what the force created by that pressure can give you. So you can levitate this small spheres, polystyrene spheres, or you can even levitate some liquid droplets. But recently people put a levitator as the end effector of a robotic arm, so they did cooler stuff, such as using that levitation force to assemble things together. Traditionally, you can do acoustic levitation simply by aligning speakers. As we said earlier in the second slide, I think, you put speakers and you let them emit sound opposite to each other. So if you want to make a little levitator, you bring two ultrasonic speakers. Actually, you must be thinking, yeah, how can we keep emitting all this sound? Won't it be annoying? This is using ultrasound, so it's not audible to humans, right? So you bring these two speakers and you let them emit sound waves, and they create this standing wave, and we know from this radial force that those objects will be kept at these nodes there. If you want bigger forces, you can make a setup like this, where you have these two balls of speakers, you align them with each other, then you let them emit sound. One thing here is that the sound is emitted by the top and the bottom speakers is 1 pi or 180 degrees out of phase. The reason for that is just, if you don't do that, you will still be able to levitate. It's just that the levitation point won't be symmetric. This is the traditional setup of a levitator. The issue with this is that you will only be able to levitate things in the middle of the setup. So if you want to move this bit here, it won't be that simple as just emitting sound waves. So people came up with a framework that allow them actually to levitate this object, but also move them around. And how you can do this is by finding these phases, more complex than simply emitting sound, just turning on and sound get emitted and you get the levitation, but you need smarter to set the delays of the speaker in a smarter way. And they were also able to do these rotations, so they were able to rotate this levitated particle, but also you can even let that particle spin using this ball configuration of speakers. The way they did this, so they have a model that lets them compute the sound propagation from each speaker, and that's a function of the delay from each speaker. So once they write that form of pressure at any point as a function of the delays, they compute something called Gorkov's potential, and it's a vector field whose gradient give you the force exerted on an object at a location. And when you apply the Laplacian to that Gorkov potential, you get the strength of the force at that point. And then what you do, if you write the strength of the force in terms of these phases of the speakers, you can do an optimization to solve this inverse problem, to find the phases that allow you to maximize the strength at certain point. And those points will be called 3D traps. So they trap your particle at those points. And thanks to this technique, what they are able to do, originally we said you need 2 boards of speakers, one on top of each other. Thanks to this, as they are maximizing the force, you can even levitate this particle using a single-sided board. And these forces, as there is some optimization behind them, not simply letting sound waves hit each other, you can even create forces that defy gravity. And then we have Hirayama and colleagues in 2019. They made this cool display they called particle-based display. So since you are levitating that particle, what you can do, you keep moving it very fast enough to create what's called persistence of vision. So you start seeing a pattern of the particle's path. So if you shine light on it, you can see something in 3D like this. And they did also use the same technique to create multiple points. So one point will be trapping the particle, another point there will be sound focused, so if someone put their hand, they can feel it, and another point of pressure, they vary to the pattern of certain voice, so you can hear sound coming from a point in the air. There is no speaker, but they vary that pressure following the pattern of a certain voice, so you can hear that voice. So in this application, I kept speaking about this speakers array, but there is one limitation of this speakers array. So they are quite bigger than the wavelength of the sound. So if you want to create really complex pressure distributions, such as these images, you will get what is called an aliasing effect. This is because they don't adhere to the Nyquist sampling theorem, which tell you if you want to get full information, you need at least to sample at half the wavelength. So you get this aliasing effect. So people start thinking about other technologies. So they created what's called acoustic metamaterial. So now instead of having a speaker that you control to change the sound delays, you create some structures, materials. When the sound interacts with those structures, those structures will introduce that phase delay you want on the sound waves. There is the transmissive forma. So you have a speaker and some materials. When the sound of those speakers passes through that material, those material will introduce a phase delay on that sound. Or you have the reflective format in which sound waves hit the materials, it gets reflected, and that reflection happen after the introduction of a sound delay. Think about it, if I have a sound wave hitting a material, I can adjust the height of the material to change the relative delay between multiple waves. So we have here, Memoli and colleague, they created what they call these metamaterial bricks. So they have this labyrinthian structure, and when the sound wave passes through this structure, each structure corresponds to a certain phase delay. So the same as before, I control electronically the speaker to have a certain phase delay. Now I can make this material, each of them will introduce a phase delay. So I don't have to do any electronic. I just turn on my speakers normally without any phase delay, but as the sound emitted by those speakers passes through this material structure, I get the phase delay I want. So if for example, I compute phase delay to levitate or focus sound, I can create those phase delays using the materials. So here they put this structure that contains many bricks. Each bricks will have a corresponding delay. So they are able to shape the sound field and levitate a particle. So that was an example of a transmissive metamaterial. So sound passed through it to get this phase delay. Another option, as I told you, is the reflective case, the reflective metamaterial. And here you will have this material of different heights, and depending on the height, you will get a specific phase delay. Think about it, if I have two materials with a height difference, if the sound wave hits this one and get reflected, it will arrive quicker than the next one, because for this one, it has to travel more than take more time to arrive at the same point, right? So this principle allows to create the same effect, such as levitation or touch sensation, by creating those phase delays we want. So we have Pratt and colleagues. They created what's called a manually reconfigurable metamaterials. So here you have this reflector. So they are just pins that slides up and down. And if you want to get a certain phase delay pattern, you can 3D print these plates, and you put them, you introduce this phase delay across the surface. And what they did, they compared the performance of this metamaterial plates against the speaker's arrays. And as we can see, these metamaterial plates, as their elements are smaller than half the wavelength, they are able to create sound pressure with higher fidelity compared to the speakers. So basically the speaker, if you want to do a focused sound or a trap, which is just a point where sound gather together, they are fine. But if you start doing more complex sound pressure distribution, you need a better technology. So let's speak about the cost of these devices. So let's imagine the case of the speakers, phased array transducer, and the case of a reflective metamaterial. So the speaker, for each speaker, you need a controller. You need a shift register to vary the phase or delay those signal. You need some amplifiers, and you need to connect each speaker to a controller. So if you have 256 speakers, you need, for example, an FPGA with 256 control points, and that's quite expensive, right? And if you are speaking about a reflective metamaterial, if you want this reflective material to adjust the height of the element live, so what you need to do, you need to put stepper motors behind them, so you push them up and down. So for each element, you need a motor driver, plus control signal. So the cost of these devices is proportional to the number of elements you have. Basically, this slide is to introduce you to the next part. Let me know if you have any questions, so I can move to the next part. Yes, tell me.
One quick question, because you said that you can 3D print like these parts. Yeah. And I was questioning like how precise you need to be, and is it like easily possible with like any 3D printer, or do you need special 3D printers for that?
So when we did print these elements, we used the normal 3D printer, the commercial 3D printer. We didn't use any fancy 3D printer or anything. The most important is that you print with, how can I say, because in the 3D printer you have setting of how much you feel the material, so you need a high feeling because you want the sound wave to get reflected on all the face of each element. So there is no requirement, it's just plastic. When the sound hits it goes back. But someone can say you need also to read about the material you are using for printing because it has different acoustic properties. Yes?
I guess this is also related to the wavelengths, right? So,
yeah.
So what is the wavelength here you are using here?
Sorry?
What is the wavelength?
The wavelength is related to the speed of the wave, but also to the frequency of the wave. Is how big is the wave.
Yeah,
so
what is the range like you are using?
Here we are using a frequency of 40 kilohertz, and the speed of sound in air is 343 meter per second. You can compute divided by.
Do you have a reason to choose this, or it can?
The reason why we use 40 kilohertz is because, which is ultrasound, is because it's not audible. It's not you can't hear it. Otherwise, this technology becomes annoying if you hear it at the same time as opera.
Why not go even further, even higher?
You can go higher to higher range, but I would say this is the speakers that are commercially available. Maybe there is a cost element to this. I can't answer this precisely, but this is what generally people in the field use.
So I think if you go higher in frequency, you need to make it even smaller, and you already have problems making it smaller.
exactly. Yeah.
My question was the 3D printing essentially, because you have grooves on the surface. I mean, you're not printing like the surface in a planar fashion.
Yeah.
Do those grooves play some like part? Because I mean, there are lines on top.
You mean the separation between the elements?
Yeah.
They will definitely play a role, but it's if you compute the surface of those separation divided by the whole surface of the sound modulator, it become negligible. Okay. Right. So there is an effect. I agree, but it's very small, right?
Yeah, another quick question about Levitation stuff. How many freedom of control you can control the particle? Issue the particle can move, like straight, can rotate.
Yeah.
Can you do moving sidely and like 6x freedom of control, or just with some limitations?
I think there is some limitations. Yeah, there is some limit. You can't do all the movement you want.
So maybe some trajectories you can't really control the particles moving like those trajectories.
Yeah, for example, but also there is the element of speed. If you are moving the particle very fast, you can't suddenly change it to. So if you want to do a star, for example, shape, it will be quite difficult. I know people are working on the algorithm to make them better at handling these cases of sharp edges. Yeah, there is some work being done there. Yeah.
Okay, cool. Thank you.
So now I will switch completely the topic. So let's imagine you want to make a bet with your colleague to tell them which speaker they will definitely have at home. What will be your choice? Is it like an LED display, OLED display, 7-segment display, or curved display? I know you have a curved display. I saw it in the office. Except Giovanni. Don't bet with Giovanni. Which display you think they will have at home? Definitely at home, if you want to make a bet. 7-segment display, right? That's the right answer. So why you think it's... so if you go to your home, you will... Maybe you didn't notice this, but if you do search in your home, you will find 7-segment display all over. So you find them in the washing machine, a dishwasher, microwave, thermostat, air fryer. Wherever you search, almost all devices, the fridge, the oven, will use these displays. Why you think is cheap? They are cost effective. If you want to show number, you are not going to buy an OLED display just to show numbers, right? If you want to show just number and character, you can use these simple speakers that have, for example, the 7-segment display. It can control 7 binary light emitters, and using that, it's enough to show a lot of number and some characters, right? There are also applications of this spatial sound modulation where you don't need to control the sound as you want. It's just you want to do you want to deliver some limited number of acoustic pressure distribution. You don't want to shape the pressure infinitely. You just want to have, let's imagine in this case, if you want to let a user fill, probably a deaf-blind user, to fill in which floor they are, and you want to provide that as a touch sensation, you can just shape the sound in the form of a G, ground floor, first floor, second floor, and third floor. You don't need to be able to shape the sound in crazy patterns. It's just these 4 patterns that you need to deliver. So let's imagine you want to do this with a reflective surface. So you have a transducer emitting sound on the surface. You want to play you want to control the heights of the element of the surface. So the G, the 1, the 2, and 3, and this is the phases or the heights of the elements, how you need to control the element. So in this case, with the same idea of this segmented display, we did the work where we try to create segmented spatial sound modulators. So traditionally, as we saw with the speakers or the other technologies such as the transmissive and the reflective metamaterial, people use this setup. Speakers that are all shaped the same, these bricks, they are all shaped the same, and and they uniformly distribute them, and that's the traditional spatial sound modulator. So what we wanted to do here is create this segmented SSMs. So they are made of elements, units that are of different shapes, and they are placed differently. The question is how to design such elements. So let's imagine you want to create a segmented spatial sound modulator that has an area A, and it has n number of elements. What we mean here by elements are, let's imagine in the case of a reflective metal surface, are the elements you push with motors. So if you reduce this number, you are able to reduce the cost. But you don't want to do it randomly. You want to shape those elements according to the requirements of your application. For example, here I want to shape my elements in a form that allow me to reduce the number of them, but also not have poor quality of the distribution, right? So we need a method that allow us to shape this element in a way that maximize the quality. So we need to decide about what's the shape. Let's imagine we have a square spatial sound modulator. What will be the shape of each of these elements? So I tell you, okay, this is this square of, I don't know, 20 centimeter by 20 centimeter. I want you to shape me the elements that I want to push up and down using my motors. To do the G1, 2, 3 example. For that, you need to give me the shapes, but also these phase delays, this height of the element I need to apply to get these pressure distributions. Sorry for putting one equation. So that will be my own equation here. Yeah, so you want to find the shape such as you maximize the quality of this pressure distribution that we are calling here acousto-holographic images. This problem is NP-hard. Think about how many ways you can split a surface into. It's infinite ways of splitting the surface. If I tell you split this surface into an element, there is infinite amount of possibilities, right? So these problems are NP-complete problems, and they generally require it to find the optimal solution. You need to do an exhaustive search. Since the number of possibilities is infinite, so this is infeasible, so you need to solve them heuristically. So people generally think of heuristics such as genetic algorithms, but in this particular case, it's challenging. The reason why it's challenging is because for genetic algorithm, for example, you can have candidate solutions. In this case, a given way of splitting the surface into an element. Then you need to find the phases. You check if when by phases I mean the height of the element. You need then to check what quality you get and decide if this candidate solution is good or not. If you know a bit about evolutionary algorithm, you need to evolve those solutions to get better quality each time. And there is no method for finding the phases of crazy shaped elements. All the methods that exist, they assume this uniformly distributed element of small size, and they are able to find you the phases. So instead of starting from the solution, what we did here is start from an ideal solution. So what we do, we assume initially our surface is split into m by m little elements. Then we say, okay, how imagine we have this surface. What will be the phases that each of these elements apply, or the delays that each of these elements apply to the incoming sound wave to get our acousto-holographic images, which are the G1, 2, 3. Then we apply an iterative phase retrieval algorithm, and we find those phases. So now we have this surface with a lot of elements. Starting from that, we want to start putting elements together to create crazy shaped elements. So what we do, we organize data from this phase distribution into a format that is appealing to unsupervised learning or clustering algorithm. Once we organize it in that format, here each row represents the delay that each row is an element, and each column is the delay that element must apply to the incoming sound wave for getting a particular distribution. Then we give that data to an unsupervised learning algorithm that cluster this data into combination or aggregation, groups of elements. So it groups elements together, and our way of grouping elements together here is those that do generally the same thing. So we have a similarity metric that allow us to judge if grouping certain element is good or bad. Generally, you group elements when they are doing the same thing. Those you can, so let's imagine 3 elements that always introduce the same phase delay to the signal. It makes sense that you put them together and then you actuate them together with the motor to have that same phase delay. And we have been able to introduce some constraints, such as saying, I want only to group elements that are adjacent to each other. So contiguous elements. I don't want you to tell me these elements that are far from each other can work together, because if I want to actuate them with the same motors, that can be physically challenging. Finally, instead of doing, as I told you, it's not really possible or nice to do phase retrieval for crazy shape element. So what we do in our approach, we can infer the phases of these segments, you can call them here, these groups of elements, starting from the phases you found initially for these uniformly distributed elements. We tried to apply that with our G123 example. So we created this experimental setup where there is a single speaker striking sound at our metamaterial surface, and we want to show an acousto-holographic image there as shown in the setup. So first what we did, we have found what's the phase and amplitude of the sound wave hitting the surface. Then we did a phase retrieval to find what's the height of the element we should apply to create of each of the G123 elements. Here we show how this pixelated version, what images this pixelated version will output. That will help us check if our segmented, the quality of the distribution that our segmented element can show. Basically, if I create this segmented structure with this phase delays, I can propagate sound on it, measure the sound, and if I want to say how good it is, I can compare it to the best pixelated version. So that best pixelated version that contain uniform high number of individual element, give me the best image, so I can compare the image I get on my segmented surfaces against it to say how good they are. And there are some image processing metrics such as SSIM metric that can tell me the quality. Here I'm plotting the quality against the number of elements of my surfaces outputted by the method. So, and then I'm comparing them to naively segmented approaches. These naively segmented approaches basically cluster pixels that are together into 2x2 elements, 3x3 elements, 4x4 element. And we can see here that our approach, this is a Pareto curve. So our approach for the same number of elements, it can output higher quality images than simply naively joining elements together. And you can see here, so this is the images outputted by our approach. All these 3 solutions have 256 individual elements. This is the one outputted by our approach under no constraints, so 2 elements far from each other can constitute a segment. And here we impose a constraint to say that only elements that are adjacent to each other can be grouped. And in the last one, we do this naive segmentation where we join 2x2 elements. So each 2x2 pixels, they become a single element together. And you can visually see that we are superior, our approach is superior than this naive segmentation. We have done this was actually simulations, And then we validated this physically. So we built this 3D printed plates of the different state. And we have here our setup with the speaker striking sound on the surface. And then we have this robot that has a microphone at the end, so it moves and measures the pressure. So we can measure this pressure distribution we created. And again, our approach is outputting distribution that are closer to this pixelated, or as we call it, the ideal solution. So we are closer to the ideal solution than the naive segmentation approach. We have also done this in the multi-frequency case. So here we are using speakers at different frequency. So for each frequency, you need a different phase signature or phase delays to be applied through the elements, right? And we wanted to create one meta surface that, as the source is changing frequency, it can still show this pressure distribution, showing here the letter U, UCL. And again, through the Pareto curves, we see that our method outputs superior segmented surfaces than the naive approach. And we have done a scalability analysis in which we applied our method to cases that have different number of images. And as you expect, we will get less good as we increase the number of images. So if you have a 7-segment display, if you start telling it to output images, you won't see anything. This is basically the same thing. So if we add a large number of images, we are not able to get this low number of segments and maintain the quality. Then we modified our approach to, now we were gluing together or combining elements that generally do the same phase, apply the same delay to the waves. So now here we have improved that method to even account for the differences. So if two elements always do the same, not the same thing, but at the same difference, we can glue them together and construct them with a difference. Then we built a device with motors. So in this work, we have actually added the motors and measured the sound waves out, the sound distribution outputted by our method. So we used it for creating this focus, but also for levitation. So on the bottom we have our reflective meta surface, and on the top we have an array that emit sound.
We showcase combining static and dynamic elements.
We have also explored the case where you have some elements that always remain static, while others are dynamic. So you can even reduce the number of actuators because the static elements don't need a motor. You can construct them as they are, and you keep them in that way without having to push them up and down. Yeah, this is the end of the second part, and I want to end it by thanking my co-authors, Professor Sriram Subramanian, PhD student James Hardwick, and Diego Martinez, for the help they gave me, especially in hard COVID time, through Teams and teaching me and helping me to do things in an area that I didn't know about at that time. Do you have any questions before jumping to a third part, where I will ask you more questions than you ask me in the third part? So the reason why Giovanni invited me here, because he thought that this technology of using sound to give the sense of touch or levitation could enhance or add something to the setup that already exists here. So I took this video from YouTube. Yeah, this guy has put this setup of the locust, so I was fascinated by. So I thought that adding this, I don't know what you think about it. I'm not an animal or locust expert, but I think you can enhance this by giving this sense of touch. For example, when a locust interacts with another one, virtually you can give that. So with this, by focusing sound at the right places, you can give them the sense of touch. Or in another setup, you can even put food in that environment, and as they approach the food, you can levitate, not trees, just little grass probably toward them, so they can probably eat that food, right? And this you can do it with this controllable spatial sound modulation. So I want to hear more from you about what do you think about applying this technology. I know that I did a bit of research. I know that locusts also here, probably in low frequencies like 5 kilohertz to 10 kilohertz. I don't know if this technology at 40 kilohertz will disturb them. That's something you can tell me about. Yeah.
But the focus of the energy at one point.
Yeah.
But that's good enough to levitate something that's put at that point. But that doesn't mean there aren't other foci around it that would potentially interfere, especially if they were in the same plane as the stimulus you're trying to present. So that's question number one. And question number two is, you explained earlier that for humans, you're not really detecting pressure. It's an illusion of pressure based upon how our sensory system detects the frequency at which our sensory system converts this into a perceived pressure. Now, insects are a very, very different sensory system. So what do we know, if anything, about how they detect pressure? And would this same trick work on them, or would it have to be modified?
Yeah, for the first point about this having multiple focus points. So what people do, so if I come back to slide earlier, so I told, for example, in the touch sensation one, so what people do, they account for that interference while doing the optimization. So here they add some constraint to maximize. So the interference between the points, they make it into constructive interference. So they add some term to the optimization to get those points constructively interfere with each other. So they add it. So there will be destructive interference to some level, but at least they minimize that and get it into constructively interfering with each other. So if you want to have multiple. For the frequency of locusts or other animal, I don't know. That's something I thought about. I said, okay, if humans detect at 200 to 300 hertz, I don't know what animals. So someone has to study at what frequency they react. Yeah.
So this is actually easy to measure. So we know the companion phosphocilla of insects. We know how they test that.
Like how they feel pressure. It's also phasic receptors that they also respond to change. And I think actually it's relatively easy to test. So if this is something you want to test, but also throughout the talk, I was also thinking the same. This would be amazing to apply tactile stimulation with this method. So I think it's really wonderful. I had just one question related to that. Could you also modify the kind of the softness of the imitated object by how focal or how accurate is your focal location?
You mean how strong or?
No, so I think like if you imagine that you touch something hard, then you would imagine that the pressure focal point will be very precise, but if it's something soft, you know, to measure you would have to move, and then if it's a softer object will be perceived if the focal stimuli will be less sharp. Does that make sense?
It does make sense, and it's a great idea, but I don't know how to do it. That's the honest. But it's a great idea. I think people will like to give this sense, but I don't know how easy it is.
You can change this.
Yeah, you can. You can change the strength of that point. You can change the I don't know but also the point of it where you are touching. Like when you do you can even move those points to mimic a soft object, for example. But I don't know how a human will perceive that. It's hard to or a locust even. I don't know about a human. Tell me about locust. Yeah. Yes.
Yeah, I have a quick question about the spatial scale. So everything you showed is like the speaker is right in front of the thing you're focusing, right? So is this technology possible if a speaker here and then across the room you have or is that like the limitation?
There is a limitation because as these sound waves propagate, they get attenuated. There is not the pressure going to infinity. So the same as we speak. If you speak here, not everyone will hear you far away. So there is that element. So there is a limitation. So people use also other sound frequencies to get higher. So they can even create. Here I didn't speak about all the application, but people create application in far field. For example, creating a noise. They cancel noise around the head of a person. without anything. You don't need to wear anything, and they cancel noise. That's a far field application, but it uses lower frequencies. Yeah.
And what about underwater? Can you put the touch sensing also to fish?
You will, this works the same. The technology will work, underwater. So sound wave will propagate differently with different measurements because.
I was going to say the speed of sound is about 4 or 5 times faster.
Yeah.
Water, it's about 1.5 kilometers
a
second, which will make it more challenging, no?
Yeah.
Also, making anything underwater is more challenging.
I'm thinking how you can put.
When this relates to a question I had before, is reflections of the tank makes doing acoustics in underwater environments extremely challenging. But similarly, in the virtual reality environment, you've got that bowl as the reflective surface. You've got these screens as reflective surfaces, and so making it acoustically achievable is going to be much more challenging even in air, I think.
Underwater it will be, you need to do a different computation, but I don't know also how this focus point will act underwater because the pressure is different. So there is some thinking, and that's research. There is some work to do, some measurements to do. So yeah.
Can you do vortex structure like just in the air? And can you do vortex structure like make the particle moving like a vortex?
I don't know. I'm not sure. I'm not sure of this, so I can't answer this. But you can, depending on how you apply the force. So if you compute the force to move the object as a vortex, you are able to do it. So it's.
And also for this, adding constraints. Is there any chance you can't find under some constraints you can't find the solution? Then you can't do that. Is there any theory can make sure? Pretty sure, whatever constraints there, you can always find the solution there. Or is there any chance you can't really find as much?
Probably there is a chance that you can find. For example, if the focus points are larger than the speakers you have, it will be hard to meet them. So you have.
Is there any theory can tell us, for example, what kind of pattern we can, what kind of constraints?
There is a theory behind this. So you are able to write this here. I'm simplifying it, but you are able to have a mathematical expression of these things that you can analyze analytically to see if you can solve and you cannot solve. Here I didn't want to throw equation because I think I didn't.
And realistically, if we really think about the scenario you show in the video with the ball, this ball in the middle wouldn't create some reflection, some issues?
Which you mean?
Because in the video you show here, the space is pretty.
This one
is empty, right?
Yeah.
There is nothing. But we have in the middle an animal walking on top of a ball. So wouldn't be.
No. It could be. It could be that the ball reflects the sound, and probably you can account for it. Because while you do so basically when you write the analytical expression of the sound, at a certain point you can say. This is the sound coming from the speaker there, but also the sound reflected back. So you count for that in analytically. So that's how people do. Actually, they are doing now with object in the middle of this to show, because they want to do 3D printing using this technology by moving material that you shine light on it and it gets solid. So they are thinking about this element of having an object in the middle. And that's basically you account for that reflections in the computations,
And can you potentially also bring sound only to some specific animals? I mean, audible sound that can be heard only by somebody and not by the person next to me? Like we are here all in the room, but you send some sound information only to.
There is an application of this called directional audio. So there is some companies making speaker using this technology. They put them in museums, for example. So if you sit next to a piece of art in a certain range, you will hear about that piece of art. If you step to other place, you don't hear. I don't know exactly I didn't look at how they do it exactly, but there is an analogous case to this, which is this directional audio. But I don't know exactly. I haven't looked at it, how it works,
So, well, I guess if there are no further questions, we can first thank the speaker again.
Thanks. Yeah.
So thanks a lot for coming. Next seminar is in 2 weeks. So thanks, everyone.